Hello, welcome back. In our last of the week one problems, we're going to prove that being a bijection is equivalent to being an invertible function. So let's write down what these things mean. You're always going to find it very helpful to know what things mean when you try to prove things. So at the top of the screen here, right, we would like to understand what it means that f from s to t is a bijection. And at the bottom of the screen, well, we want to know what it means for f from s to t is invertible. And hopefully we can find our way to combining these things in the middle. So what does it mean that f is a bijection? So this is equivalent to saying that f is injective and f is surjective. Okay, well, we better understand what those things mean. So in the previous video, we talked about how an injective function was it was a codomain condition, right? You look at each element in the codomain, and there needs to be one arrow going into it. So when we drew pictures, we drew something like this. We said, okay, you got an S and a T, and you have some points over in T, and to be injective, you can't have more than one arrow going into each point. It's okay to be missing something, but you can't have this second arrow going into that same point. So being injective, right, means you only have at most one arrow going into a point. Now the math language that we'll tend to want to use going forward is to say that each element in the codomain has at most one pre-image. So what do I mean by pre-image? Well, we know these arrows have to come from somewhere, and let's say this dot came from that dot on the left. Okay, this dot on the left is called the pre-image of the dot on the right. Okay, the dot on the right is the image of the dot on the left. The dot on the left is the pre-image of the dot on the right. Now, if you'd had a second arrow, right, say this second arrow coming in, it came from another dot, then this point on the right would have two pre-images, right? That's not allowed with an injective function, but in general, that for a regular function, that's possible. You can have more than one pre-image. Okay, so but the way we can say, right, what does it mean for f to be injective? We can say each element of the codomain, so of T, has at most one pre-image. Okay, how about surjectivity? Well, surjectivity was saying that every element in the codomain has to have an arrow going into it, right? Could have more than one, so this red line going in, that'd be okay. But you have to have at least one. So we're basically saying surjectivity means each element of the codomain T has at least one pre-image. Okay, but the combination of these then is very easy to determine, right? If you have at most one pre-image, and if you have at least one pre-image, then the combination is you have exactly one pre-image. So saying that f is a bijection is equivalent to saying that each element of T has exactly one pre-image. Okay, so let's pause on the upper side of this for a second, and let's talk about the bottom now. What does it mean for this function to be invertible? Well, definition of invertible is that there's another function which goes backward. So this is equivalent to saying there exists a function g that goes from t to s. So you switch the domain and the codomain such that if you compose the functions, so say you first apply f and then you apply g, so this would be a map, right? F goes from s to t, and then g goes from t back to s. So this would be in total a map from s to s. All right, so that's what g composed f would look like. And this should actually be the identity map on s if you're going to have an invertible map. And the other direction needs to work similarly. So if you compose first g, which goes from t to s, and then f, which goes from s to t, you should get a map now from T to T. And furthermore, that map from T to T should be the identity map. Okay, of course, you just pick arbitrary maps, that won't work. But if f is invertible, this is what needs to happen. There needs to be a G which will satisfy both of these properties. All right. So the question, right, then is how are we going to build such a function, right? How do we get this G? The beauty of what we have up above is we have a way of starting from an element of T and getting an element in S, right? Because when we say this has exactly one preimage, right, this is in S. So we have a way of taking an element from T and getting a unique element from S. We have a way of building a function, right? So this appears equivalent to saying there exists a function G from T to S, right? So you actually know what it is, such that, well, it's not just that we have a function, but it's even better, right? We know that it's the preimage under this function f, right? So the preimage under f, such that, so what happens to, let's say I take some element over here in T, oops. So if I take some element, I know that it, right, has a preimage, some element that was sent to it by f, right? So let's say we had a dot, all right? And so f, maybe it sends x to y. All right, so I choose some y, and let's see what happens. So I have some, if y is, say, in T, then there exists a unique x in S such that f of x equals y. And, well, what is this function g doing? Well, g sends y to x. Okay, so this is how we're going to get this composition being the identity map. All right, because we can see now, if we compose, so let's say we applied g to y, and then we apply f to that output. We know that g evaluated at this y is going to be x. But x gets sent to y by f. And so this tells you that the composition of f with g doesn't do anything to y. It's the identity on the set T. What about the other way around? So what if I do g composed f and I evaluate this on, say, x? Remember, x was our element of S. So this means we do g of f of x. But we know that f of x is y. So this is g of y. But g sends y to x. And so in total, g composed f doesn't do anything to x. G composed f is the identity map on S. Okay. Now you might say, well, this was just for a particular one, right? Well, no, right? We know that for every, right, or each element of T, we can play this exact same game. Okay. So we can see here that even though these sound like they're very different definitions, right? Being a bijection is about injectivity and surjectivity, and invertibility is about the existence, right, of a function, which, if you compose it, is giving you the identity in one direction, the identity in the other direction. Actually, they're the same thing, right? And just maybe one last bit of commentary. If you go back to the definition of function, right? Function was saying you need, for each point in the domain, first, there must be at least one arrow going out, right? You can't have some, if you have a dot here with nothing coming out, that's no good. But to be a function, right, to really be a function, there also can be at most one arrow coming out. So in total, there needs to be exactly one arrow coming out. To be a bijection, that's just saying the same thing on the codomain side. For each dot in the codomain, there needs to be exactly one arrow going in. Well, if you just take all of those arrows and turn them around, put the arrow tips going in the other direction, that's your function, right? That's how you get a function when you have a bijection. You just turn the arrows going in the other direction, and that's your inverse.